Welcome back to InGuide. We are focusing on search algorithms and specifically binary search. Today we'll describe another problem, which is the fourth problem in the series. Let's look at the problem. The problem is to find all the elements that are at the intersection of two sorted arrays. So we have given two arrays, both are sorted, and we have to find out elements that belong to both the arrays and without duplication. So let's add that additional clause that no duplications are allowed. Let's see how to solve this interesting problem. If which is sorted, and we have array B which is also sorted. Now one very basic and simple approach is for each element of A, so basically each element belonging to A, search for the existence of the same element in the B array. So if E also belongs to B, then we add it to the intersection list, then add to the intersection list. Now, what is the complexity of this algorithm? We are going over each and every element of A. Suppose the number of elements or the cardinality of A is equal to n and the cardinality of B is equal to m. So for every element of A, we are searching for the existence of the same element in B. So the complexity of this algorithm is order of n times order of m. And now, can you do better? This is strategy 1. Now strategy 2, can we improve on this algorithm? Definitely, because we know that the arrays are sorted, so we must be making use of that clue. So since the arrays are sorted, first figure out which one is the smaller one. Suppose the cardinality of A is much less than that of B. So then what we can do is for each element of A, for each element E belonging to A, do a binary search on B. Search on B. So now what is the complexity of this algorithm? So we are going over every element of A, so that is order of n, and for each such iteration we are doing a binary search on B, so that complexity is log of m. So the overall complexity of this algorithm or this strategy is order of n log m. So this will be very beneficial if m is much larger than n, because log algorithm or this strategy is order of n log m. So the overall complexity of this algorithm or this strategy is order of n log m. So this will be very beneficial if m is much larger than n, because log of m is much smaller than m. So this is an improvement just because we know that both the arrays are sorted. Now can we improve upon this as well? So we know that the arrays are sorted, and because of that we can actually accomplish this in linear time. So here is an algorithm to do that. Now let's call the routine find intersection, okay? And the input to this algorithm are the two arrays A and B. Okay? Now we just need to keep two counters. So int A count is equal to 0, which is going over the elements of A, and then we have int B count equal to 0, which is going over the elements of B. And also keep track of the matching element. So int match is equal to some predefined number, say none. Okay, in the beginning we don't have any match. Now we just need a simple while loop here, which goes over both the arrays. So while the counter that counts the elements of A is less than the length of A, and also the B counter is less than the length of B, that means none of the arrays are exhausted, do the following. What you have to do is, if at any location, so currently we have this counter that's counting it. Now if the value at the location A with the index A count is equal to the value of the B counter, or the value of the element belonging to B at location B count, then we found a match. So what we do then is, if this is true and this element is not found before, is not equal to last match. Okay, why this condition is needed? The reason this condition is needed is we don't want duplicates in the intersection array. So if both the arrays contain some duplicates, we don't want to repeat that in the intersection array. So that's why we need this check. Now why a single check will do? Because this is sorted arrays, so they have to be either the last element repeated many times, or it can be only once present. And since we are going incrementally and traversing both the arrays simultaneously, if we simply check that the element value is not equal to last match and then only enter, that will take care of duplicates. So in this case we say, okay, we found it, else case we simply check whether the value in the A list is less than the value in the B list. If that is true, then only increment the A counter. Otherwise, increment the B counter. So you can see that this whole algorithm traverses the A list at most once, so order of n, and then it traverses the B list almost at most once, so order of m. So overall complexity is order of n plus m. So this is by far the most efficient algorithm of the three algorithms that we described today. So strategy 1 was a brute force order of nm, strategy 2 was little bit improved order of n log n, and 3 is order of n plus m. So that's it for today. We'll get back with more algorithms, especially binary search that we are dealing with as part of this series. Look forward to see you again. Bye.